Welcome back to a new video, and this one is about boundaries and how we can use the principle of superposition that we just learned about in the past couple lectures to account for boundaries, whether there are recharge boundaries, so let's say a stream, for example, or there are no flux boundaries like a mountain, for example. So here's again an example of a recharge boundary where we do have a stream here. Let me do it blue maybe, where we do have like a recharge boundary. So let's say a stream, right, that maintains that head at a constant level, and then now this is recharging into that aquifer to the left. So if we have our pumping well here, you can see how this is modifying basically our setup. So this is very similar to a leaky confined aquifer that we've done before, but now instead of using those leaky confined equations, etc., or finding that steady state, we can actually use that superposition principle and put an imaginary well on the other side of that boundary. So the principle here again, if we have a pumping well here and a recharge boundary here, the idea is to put an imaginary well on the other side of the boundary at an equal distance away from that boundary. So again here. So this is right. So if we're at the distance A from that boundary, if our pumping well is at a distance A from the boundary, we put an imaginary well at a distance, 2A from our well, or another distance A from the boundary on the other side of it. And of course, this well needs to compensate for our well. So this one would be a recharging well, meaning we're putting water into the aquifer to compensate for that pumping at the boundary. So what we want is again that at the boundary, the effect of our well is not felt anymore because we have that constant head, recharge boundary. So here's a little graphic representation of this, right? If we have a river in the middle and we have a pumping well 50 meters from our river, basically we add another well, imaginary well, 50 meters on the other side, and that would be a recharge well to account for the fact that this boundary is a recharge boundary. It's providing water to the system. Okay, so if we, again, the image well theory is an application of the principle of superposition, as I said, and it allows us to represent simple types of boundaries for an aquifer. Theory is applicable for transient problems as well. For example, if a production well is adjacent to a constant head boundary, so just like we've seen before, the drawdown is given by, and again, this is the well function, so this is the time, the transient solution for the wells, so Q over 4 pi t, and then the sum, which is W U real, so little r stands for the real well, minus WUI, and the little I stands for imaginary, or right, image solution, if you will. Again, as time goes to long times, right, at long times, the Jacob approximation can be used, and we've seen that before. So when the Jacob approximation is valid, then we can use these, approximations here. And then ultimately, right, at even longer time, the imaginary well, we can also use the Jacob approximation. So now we can write this and this, right, if we can use that approximation for both, and then realize that when we subtract, right, ln of x minus ln of y is ln of x over y. So a lot of those, basically all those constants are going to disappear. The only difference is, again, the radius, right? The Ri and the Rr, the radius of the real well versus the radius of the imaginary well. And so we're left with that very simple equation here, where the drawdown in our well is Q over 2 pi t, natural log of the ratio of the distances, okay? So very simple, and notice that this is basically our theme equation, or TM equation, right? Team equation. So this is our basic equation for groundwater flow to a well that we derived in the very first lectures on these well hydraulics lectures, right? So when we do the mass balance around a well, this is what we end up with, and when we consider, two wells working together, we end up with the same system, a very simple system. Now for an unconfined in an unconfined recharge boundary. So if our aquifer is unconfined, now of course we end up with our squared head, right? And we can write this. So notice how now we lost, of course, the transmissivity because we don't, again, the aquifer thickness, right, is variable now. So the system is slightly different. But again, notice that how we end up with, again, an equation that's similar to the team equation, except it's for an unconfined well, where now we have Q over pi K, not T, and the natural log of the ratio of the distances again, and the squared here on the left-hand side. So very simple equations that we can use for two wells. So again, an example, a simple example, a well that has a 20 centimeter radius produces 550 cubic meters per day from an unconfined aquifer, right? And the hydraulic conductivity is 10 meters per day. The well is located 250 meters from a river. The saturated thickness is 30 meters. What is the drawdown at the well? And you can see that we can use this equation here to, just plug in basically. So the saturated thickness, right? So the head before we start, basically the head before we start pumping is that HR, or the radius of influence, right? This undisturbed thickness of the aquifer, that's HR. So we can calculate H equals square root of HR squared, so that's your 30 meters, minus Q over pi K ln R over R, okay? And all of those things are known, so you can just plug in and find that the head in the drawdown, in the well is going to be 27.6 meters. So again, you can use, this principle either in confined or unconfined aquifer for steady state or transient state. So very powerful way to account for boundaries. So again, in that next short lecture video, I will show you another example with rivers coming off a mountain range, out of a canyon from a mountain range, basically into an alluvial valley, and then how we can represent this with those imaginary wells. Thank you.